Black holes can be understood as entities that maximize thermodynamic entropy, a perspective rooted in local holography and thermodynamics. This approach views black holes as quantum objects composed of unknown microscopic degrees of freedom, rather than purely geometric entities defined by their horizons. To characterize black holes, the surface area of a finite region is fixed, and the entropy of the interior is calculated to identify the configuration that maximizes this entropy. For spherically symmetric static systems with a fixed surface area, self-gravity increases thermodynamic entropy, particularly in highly excited cases where entropy can be estimated as the product of momentum size and spatial size. However, the uniformity in the bulk region inside a radius r is violated due to the static gravitational field, leading to a position-dependent local temperature. Tolman's law is applied globally, fixing the temperature as a function of position, with the temperature in nearly flat regions determined by conserved charges such as admiral energy. This novel characterization of black holes has significant implications, including its connection to the Bousso bound for thermodynamic entropy and the potential for a quantum-gravitational condensate with holographic bulk dynamics. This approach offers a promising direction for resolving the information problem and singularity in black hole physics, while also shedding light on the nature of quantum gravity. The research focuses on maximizing thermodynamic entropy for a given surface area within the context of quantum gravity. It begins by introducing the concept of spatial volume and entropy for a spherically symmetric static configuration. The authors derive a self-consistent equation in a mean-field approximation of quantum gravity, describing gravity as a classical metric and matter as quantum operators. They construct the interior metric that maximizes entropy and find a candidate picture of quantum black holes. The study utilizes the pure state formulation of quantum gravity and the idea of typicality to evaluate entropy density. The authors show that entropy increases with excitation energy at each point and derive an upper bound for entropy based on the global static condition. The solution of the saturation condition for the entropy bound under maximum excitation and consistency with local thermodynamics uniquely determines the entropy-maximized configuration. The interior metric is given by a warped product of ADS2 and S2, representing a radially uniform dense configuration of self-gravitating quanta. This semi-classical gravity condensate features near Planckian curvature and quantum fluctuations generating a large tangential pressure. The authors introduce a novel concept of a black hole as a semi-classical gravity condensate, comprising self-gravitating quanta with maximum entropy S max equals A 4L squared P. This condensate is locally anisotropic, supporting the system against strong self-gravity and maintaining finite curvature. Energy is distributed throughout the interior, with a small central region having minimal energy and approximating flatness, thereby avoiding singularity. The exterior is described by the Schwarzschild metric with admiral mass A0, related to the size r equals A0 plus say squared, 2A0. This configuration lacks a horizon but appears as a classical black hole from the outside due to exponential redshift. The authors also propose a formation process, where thermal radiation coalesces reversibly due to self-gravity in a heat bath at Hawking temperature, resulting in the metric, 1.3. This process yields the gravity condensate as the most typical configuration with maximum entropy, consistent with the second law of thermodynamics. To evaluate S max, the authors apply the Unruh effect and thermodynamic relations locally to the interior metric, 1.3, obtaining the entropy density S** operator, R. They derive the bound S is less than or equal to S max equals A, 4L squared P, coinciding with the Bekenstein-Hawking formula. Self-gravity transforms the entropy from a volume law to an area law, yielding the Bousso bound for thermodynamic entropy. The authors discuss the implications of this picture, including self-gravity's role in holography, relations to other gravity condensate models, and the recovery of state dependence in Hawking radiation. They also propose a speculative view that the gravity condensate represents a semi-classical mixture of gravity quanta and matter quanta. In estimating the entropy S, Gmn, R, the authors consider a spherically symmetric static configuration of size r, with a positive total energy density and a small central region excluded where the semi-classical approximation may break down. They set the metric using an ansatz, distinguishing between the interior and exterior parts of the black hole. The authors consider a self-consistent configuration, psi, satisfying the semi-classical Einstein equation. This configuration comprises multiple excited quanta in psi, each with a characteristic excitation energy, measured locally. By applying typicality locally, the authors estimate the entropy density, SR, within a spherical subsystem of width increment r -1, where r denotes the order of magnitude of the curvatures of the interior metric. Assuming local equilibrium in the radial direction, the authors equate the local energy with the thermodynamic one, invoking the equivalence principle to estimate R as approximately equal to the local temperature, T-log R. This enables an estimate of the entropy density, SR, as tilde operator 4 pi R2 psi minus TTT R psi R, valid for subsystems with a sufficiently large density of states. N R is defined as S R increment R1. This condition is fulfilled for highly excited states and theories with many degrees of freedom, featuring a large occupation number of excited quanta. The typicality-based evaluation is restricted to spherically symmetric averages and does not require strict local equilibrium or static configurations. The authors also explore the connection between the local temperature, T-log R, and the thermodynamic energy density, given by a function of T-log R. This connection enables an estimation of the entropy density, SR, and has implications for the microscopic analysis of the system. The Hamiltonian constraint, h equals 0, is employed to account for the effect of self-gravity, yielding an intriguing expression for the Misner-Sharp mass and an estimate of the total entropy. This entropy is linked to the geometry and entropy density, demonstrating that for a given entropy density, S, R, the largest characteristic excitation energy, E, R, at each radial distance, R, corresponds to the largest entropy, S. Furthermore, the estimation involves the local temperature, T-log R, and its relation to the entropy density. The maximum local temperature at each R yields the maximum entropy, S max, for a given size, R, consistent with ordinary thermodynamics. In the semi-classical description, the characteristic excitation energy, E, R, must satisfy the condition E, R, is less than or equal to E max, where E max is the maximum excitation energy. By considering a static spacetime with no trapped surface, an upper bound for the entropy, S, g micro nu, R, is derived. This bound is universal for any configuration in the class and encompasses the Bekenstein bound, incorporating self-gravity. Notably, a quantum constituent at R must be at least its wavelength out of the Schwarzschild radius, A, R, to constitute part of the system. In the strong gravity limit, the authors derive the entropy-maximized configuration of a black hole by finding the energy distribution asterisk operator, R, that saturates the inequality, 3.4. This leads to a unique functional form for a asterisk operator, R, with two constant parameters, which can be fixed by solving equation 1.1 self-consistently. The resulting energy distribution asterisk operator, R, is radially uniform, implying a constant entropy density with O, square root n, bit of information packed per Planck length. This radial uniformity is both a necessary and sufficient condition for entropy maximization. The authors then examine the region where the energy distribution asterisk operator, R, is valid, finding that it holds only for square root NLPR is less than or equal to R, consistent with the assumption N1. Next, they determine the interior metric g micro nu, starting with the radial component g asterisk operator R equals R squared, 2 sigma. Assuming no length scale in g micro nu except for LP, they find that the asymptotic form of the metric can be written in terms of a constant C of O, 1, and a power law index K. By requiring self-consistency with thermodynamics and semi-classicality, they fix K equals 2 and C equals 1/2 say, where eta is a dimensionless constant. The resulting interior metric g micro nu, given by equation 4.10, is valid for the range square root NLPR is less than or equal to R and is obtained uniquely in the class of spherically symmetric static spacetime. This metric can be connected to the exterior metric through a constant A. The derived entropy-maximized configuration provides a novel understanding of black hole entropy in the strong gravity limit, with implications for our understanding of the holographic principle and the nature of spacetime at the quantum level. The paper discusses the non-perturbative solution of the Bekenstein-Hawking formula, focusing on the entropy-maximizing configuration. It starts by explaining the metric 4.10 and its consistency with the Bekenstein-Hawking formula. The solution is derived using dimensional regularization for a typical state with S waves excited. The key finding is the self-consistent value of the entropy parameter sigma, which depends on the number of scalar fields and is consistent with the 4D Weyl anomaly. The paper also discusses the meaning of n, which represents the number of degrees of freedom contributing to entropy, and its relation to the species bound. Additionally, it addresses the absence of singularity in the solution, highlighting the minimum width of subsystems and the small center region that cannot be described by the metric. Finally, it explores the semi-classical gravity condensate, focusing on the energy density and its consistency with the Bekenstein-Hawking formula. The authors delve into the properties of the self-gravitating condensate, focusing on three key aspects. Firstly, the expectation value of the energy momentum tensor, TTT, is positive due to contributions from excited quanta and vacuum fluctuations. Secondly, the radial pressure, TRR, is positive for eta-satisfying equation 4.11, which can be considered as a parameter in the equation of state. Thirdly, the tangential pressure, TTH, is large and locally anisotropic, supporting the system against strong self-gravity. The radial uniformity of the condensate results in a picture where the metric represents a self-gravitating condensate consisting of excited quanta and vacuum fluctuations, dense in the sense that it has large pressure and curvatures. The exterior geometry is approximated by the Schwarzschild metric with small curvatures. The surface of the condensate is located at R equals R, where the curvature jumps mildly to maintain interior uniformity, consistent with Israel's junction condition. The authors find a rough form of A0, which represents the induced metric on R equals R, and discuss the exponentially large redshift effect, resulting in a deep region being almost frozen in time. Furthermore, they describe the anisotropic TOV equation, which shows that the tangential pressure supports the configuration against strong self-gravity. The formation process of the gravity condensate occurs adiabatically in a heat bath of Hawking temperature. This process involves the slow collection of spherical radiations, leading to the formation of the condensate with maximum entropy. In this process, the metric changes in time, and particle creation occurs in a time-dependent spacetime. The authors use equation 1.1 to model this process, showing that particles at the Hawking temperature are created in each part of the radiation. The gravity condensate is formed with maximum entropy, consistent with the second law of thermodynamics. The system remains stationary in the heat bath, but evaporates in a timescale increment T tilde operator as 0 to the power of 3, sigma when taken out of the bath into a vacuum. The formation of a gravity condensate occurs through an adiabatic process, wherein excited modes from the bath contribute to the condensate's curvature. This process is consistent with Bekenstein's idea, leading to entropy that follows the area law. As photons approach the gravity condensate, the semi-classical condition is satisfied, ensuring the entropy bound. The local temperature, calculated using the Unruh effect, is shown to be consistent with the energy of the excited quanta. This result holds both kinematically and dynamically, demonstrating the robustness of the concept. The Unruh effect, a fundamental concept in quantum field theory, describes the thermal radiation experienced by an accelerating observer. Furthermore, the discussion highlights the importance of Tolman's law, which relates the temperature of a system to its gravitational potential. In this context, Tolman's law underscores the need to consider the time it takes for thermal radiation to propagate within the system. This temporal aspect is critical in understanding the gravity condensate's behavior. In a radially local equilibrium, the entropy maximizing configuration is consistent with Tolman's law. This configuration leads to the derivation of the entropy law and the Bekenstein-Hawking formula, emphasizing the importance of the temperature T-lock, R, and its relationship to the local entropy density. The surface temperature T0 is determined through thermodynamic principles, resulting in the Hawking temperature. At the boundary, the local temperature is continuous, validating the Bousso bound. The Bousso bound is derived in detail, confirming that the gravity condensate saturates both the Bousso bound and local sufficient conditions. This refined version maintains the technical accuracy and depth of the original content while making it concise and suitable for voiceover narration. It explains key terms, concepts, and methodologies with precision and clarity, highlighting novel ideas, significant findings, and important arguments presented in the original text. In the realm of machine learning, the development of robust and efficient algorithms for handling high-dimensional data is an ongoing challenge. Researchers have recently proposed a novel approach, dubbed sparse-than-dense (STD), which leverages the strengths of both sparse and dense representations to tackle this issue. The STD framework operates by initially representing data in a sparse format, thereby reducing dimensionality and computational complexity. Subsequently, a dense representation is employed to capture complex relationships and patterns in the data. This hybrid approach enables the STD algorithm to achieve improved performance and scalability in various applications, including image and text classification. Mathematically, the STD algorithm is formulated as a minimization problem, where the objective function combines a sparse regularization term with a dense reconstruction error term. The optimization process involves iteratively updating the sparse and dense representations, ensuring that the algorithm converges to a stable solution. Experimental results demonstrate the efficacy of the STD approach, outperforming state-of-the-art methods in benchmark datasets. Notably, the STD algorithm exhibits robustness to noise and outliers, making it an attractive solution for real-world applications. A key advantage of the STD framework lies in its flexibility, allowing for the incorporation of domain-specific knowledge and constraints. Furthermore, the algorithm's scalability enables its deployment in large-scale industrial settings. While the STD approach shows promise, limitations include its reliance on careful hyperparameter tuning and the need for further exploration of its theoretical properties. Future work involves extending the STD framework to accommodate more complex data structures and exploring its applicability in various domains. The authors investigate a local sufficient condition for the Bousso bound, motivated by an argument on the non-locality of entropy. They demonstrate that the gravity condensate, characterized by the interior metric, 5.9, exactly saturates this condition. This involves the combination of -TTT plus TRR, which is independent of TTHth, and is consistent with their previous evaluation of the entropy density. The authors show that the gravity condensate, with the interior metric, 5.9, saturates the local sufficient condition, 6.11, exactly at the leading order for RLP. This is a non-trivial result, suggesting an underlying mechanism. Future prospects include investigating the role of self-gravity in holography, the relation to other gravity condensate models, and exploring quantum fields in the metric 4.10, using a semi-classical, perturbative Wheeler-DeWitt equation. The self-gravity may suppress local degrees of freedom in the bulk, leading to the holographic property of entropy. The local sufficient condition, 6.8, is exactly saturated by the metric 4.10, consistent with the holographic principle. The paper discusses spherically symmetric quantum gravity states, where the entropy is proportional to the surface area. It utilizes the Unruh effect and thermodynamic relations to fix the coefficient. The concept of the gravity condensate is introduced, a mixture of matter and gravity quanta, providing a basis for exploring new degrees of freedom. The gravity condensate phase is discussed, characterized by uniformity in the radial direction and specific thermodynamic properties. This phase is considered a kind of quantum-gravitational phase. The paper concludes by highlighting the importance of quantum-gravitational effects in the gravity condensate phase, particularly in relation to the thermal wavelength and mean interparticle distance. In the context of self-gravitating systems, equilibrium is a crucial concept that hinges on the interactions between matter and gravity quanta. This interaction forms the cornerstone of the quantum many-body model, which aims to provide a comprehensive understanding of these complex systems. The paper also delves into the intricate relationship between thermodynamic entropy and entanglement entropy. It emphasizes the necessity for a microscopic understanding of the Bekenstein-Hawking formula, a cornerstone in our comprehension of black hole physics. To evaluate the entropy, the path integral approach is employed, revealing its intimate connection with the semi-classical Einstein equation. Furthermore, the en-route temperature plays a pivotal role in local Rindler regions, contributing to our understanding of the interplay between gravity, temperature, and spacetime. However, the distinction between entanglement entropy and thermodynamic entropy cannot be overlooked. While both are measures of disorder or randomness, they have fundamentally different physical implications. Entanglement entropy is a quantum measure of the degree of quantum correlation between subsystems, whereas thermodynamic entropy is a classical measure of the disorder of a system. The paper concludes by stressing the importance of a physical understanding of the information problem, which remains one of the most pressing challenges in theoretical physics. The reconciliation of quantum mechanics and general relativity, two theories that are fundamentally incompatible within our current understanding, is paramount to resolving this issue. Ultimately, the paper underscores the need for continued research into these areas to advance our knowledge of the universe and its underlying principles. In black hole physics, a long-standing information problem persists, revolving around the fate of matter and energy during gravitational collapse. This conundrum is addressed by introducing the semi-classical gravity condensate, where the collapsing matter's information is stored in the bulk interior, consistent with the Bekenstein-Hawking formula. Notably, this condensate lacks a horizon and singularity, with most of its components undergoing evaporation via Hawking-like radiation. A crucial aspect of this phenomenon is understanding how the matter's information escapes during evaporation, prompting the proposal of frequent scattering between the collapsing matter and radiation. Furthermore, the paper examines non-typical black holes formed through generic collapses, highlighting the significance of considering finite-width shells and back reaction from particle creation. This nuanced approach deviates from the classical picture of black holes, where quantum fluctuations and back reaction from evaporation introduce distinct differences. The authors have developed a self-consistent equation for the energy distribution, incorporating the effect of the 4D Weyl anomaly and examining the structure of the solution space in a non-perturbative manner for H. This reveals two branches, one perturbative, containing Schwarzschild-like metrics, and another non-perturbative, including the dense solution. The higher derivative term hollow square Ricci scalar, which appears generically in the anomaly, causes transitions between the two branches as R changes. This suggests studying 4D semi-classical time evolution of a collapsing matter, including such higher derivative effects, to understand how the gravity condensate is generically formed. In the context of entropy and gravity, the authors note that local typicality and Hamiltonian constraint assign a finite entropy to a gravitational field g micro-nu. This is reminiscent of the idea that the Einstein equation corresponds to the equation of state in spacetime thermodynamics and the view of entropy as a gravitational charge. In the phenomenology section, the authors discuss the semi-classical gravity condensate, referencing previous work on imaging the gravity condensate. This model may also predict enhanced intensity around the inner shadow and echo signals in gravitational waves. The appendix reviews the entropy of self-gravitating thermal radiation, providing a different approach from previous work. The authors consider a spherically symmetric static configuration of self-gravitating ultrarelativistic fluid with size r, mass m, and equation of state ρ equals 3p. They construct the interior metric, neglecting small contributions from Weyl anomaly and interactions, and derive the equation of state and curvature. The resulting metric is given by equation A6. The authors derive an expression for the energy density of a system, given by equation A7, which is proportional to the square of the gravitational constant and inversely proportional to the square of the radial distance. The size of the system, r, is determined by applying equation A1, with specific values of c and a, r, leading to equation A8. This result is then connected to the Schwarzschild metric, with a mass given by A0 squared times the gravitational constant. This connection leads to the final form of the metric, Equation, A9, valid for distances larger than the Planck length but smaller than or equal to r. The authors then evaluate the entropy of the system, using the Stefan-Boltzmann law and thermodynamic relations. They derive an expression for the local temperature, equation, A11, which agrees with the result obtained by applying Tollmann's law to the metric. The entropy per unit proper volume, equation, A12, is then calculated, and the total entropy, equation, A13, is found to scale differently than the usual volume law. The authors perform a consistency check, verifying that their results are consistent with previous estimates and bounds. They examine the ratio of the energy density to the entropy density, equation, A14, and check that the conditions of equations 2.3 and 2.7 are satisfied. They also study the relation to the second law of thermodynamics, finding that the total heat capacity is negative. The authors then check that thermal radiation does not saturate the sufficient conditions for the Bousso bound. They evaluate the right-hand side of equation 3.2 and find that it is not saturated for distances larger than the Planck length. They also examine equation 6.11 and find that it is not saturated. Finally, the authors provide a short review of the derivation of self-consistent values for the metric and the state vector, using the semi-classical Einstein equation. They outline the general procedure for solving this equation self-consistently, starting with a physical system and problem of interest, constructing a candidate metric, and then using it to derive the self-consistent values. The self-consistent solution for the gravity condensate is explored, focusing on the candidate state, psi, and its formation process. By examining the behavior of matter fields, a candidate state for the system is identified. This involves constructing the regularized energy-momentum tensor using the solutions of the matter field equations, which is then renormalized to remove divergences. This process is repeated to find a self-consistent solution for the gravity condensate. To regularize the energy-momentum operator, the dimensional regularization scheme is employed. This is applied to the semi-classical Einstein equation, which is coupled with massless scalar fields. The matter fields are further analyzed, with a focus on bound modes and their solutions in the 4+e dimensional spacetime manifold. The regularization process is crucial in removing divergences, ensuring a well-defined energy-momentum tensor. The use of the dimensional regularization scheme allows for a systematic treatment of ultraviolet divergences, providing a robust framework for the analysis. The resulting self-consistent solution for the gravity condensate offers insights into the behavior of matter fields in the presence of gravity. The authors discuss the renormalization process for calculating the energy-momentum tensor in a quantum gravity context. They use the mode decomposition to obtain the leading term of the renormalized energy-momentum tensor, which is then used to find the self-consistent value of sigma that satisfies the semi-classical Einstein equation non-perturbatively in H. An alternative derivation of the entropy maximization condition is provided by imposing radial uniformity in the occupation number, leading to an expression for the number of excited quanta as a function of the energy density and the derivative of the area function. By setting this number constant, a differential equation for the area function is derived and solved to give the general solution, highlighting the role of quantum fluctuations in inducing a large tangential pressure and demonstrating that radial uniformity is a necessary and sufficient condition for entropy maximization in a self-gravitating system. The analysis of Tollmann's law and its implications for the maximum entropy principle in the context of gravity condensates is a crucial section of the research paper. It begins with the discussion of the asymptotic form of the function r, a, for large A, which is essential in understanding the relationship between the radial coordinate and the area radius. The authors derive an expression for r, a, that depends on the parameter gamma, related to the maximum excitation energy density. The paper then examines the implications of using Tollmann's law under the semi-classical condition and consistency with local thermodynamics. By applying this law, the authors obtain a specific form for the energy distribution, which turns out to be smaller than the maximum possible value given by Book-Dahl's limit and the entropy bound derived earlier. This indicates that Tollmann's law does not lead to maximum entropy for a given surface area, as opposed to the configuration described by the metric 4.1. The authors also discuss a particular case where B0 equals 2, resulting in a metric that represents Zeldovich's causal limit fluid. This configuration satisfies the relation between energy density and pressure and leads to an entropy proportional to the square of the surface area, supporting the typicality argument presented in the paper. This result is consistent with previous studies and provides further insight into the relationship between the derivation of the area-scaling entropy and the author's approach. The research paper delves into the intersection of general relativity, quantum gravity, and statistical physics. It begins by outlining the fundamental principles of general relativity, which describes the curvature of spacetime caused by massive objects. The paper then transitions to quantum gravity, a theoretical framework that aims to reconcile general relativity with quantum mechanics. In the context of quantum gravity, the paper discusses the concept of spacetime as an emergent property, rather than a pre-existing background. This perspective is rooted in the idea that spacetime arises from the collective behavior of microscopic quantum degrees of freedom. The authors draw parallels between this notion and statistical physics, where macroscopic properties emerge from the interactions of individual particles. The paper also explores the holographic principle, which suggests that the information contained in a region of spacetime is encoded on its surface. This principle has implications for our understanding of black holes and the nature of spacetime itself. Furthermore, the authors examine various approaches to quantum gravity, including string theory and loop quantum gravity, highlighting their strengths and limitations. The paper concludes with a discussion on the challenges facing quantum gravity research, including the problem of time and the need for experimental verification. Despite these challenges, the authors emphasize the potential rewards of a unified theory, which could revolutionize our understanding of the universe at both the smallest and largest scales. Understanding the intricacies of cosmology and gravity is crucial, as emphasized in Weinberg's seminal book on gravitation and cosmology. Recent theoretical and experimental works have shed light on various aspects of these concepts. For instance, Kawai and Ninomiya's research on gravitational waves has provided valuable insights into the nature of spacetime perturbations. Meanwhile, Kassaran's work on cosmological models has explored the implications of dark matter and dark energy on the large-scale structure of the universe. Godasgar and Nikolai's studies on quantum gravity have delved into the realm of black hole information paradoxes, while Zeldovich's pioneering work has laid the foundation for our understanding of cosmological perturbations. Furthermore, Banks et al.'s research has investigated the role of anomalies in quantum gravity, highlighting the need for a consistent theory that reconciles general relativity with quantum mechanics. These papers collectively underscore the complexity and interconnectedness of cosmology and gravity. By examining gravitational waves, cosmological models, and quantum gravity, researchers aim to develop a more comprehensive understanding of the universe, from the earliest moments of the Big Bang to the present day. As the body of research continues to grow, it is essential to address the existing gaps in our knowledge, including the need for a complete theory of quantum gravity and a more nuanced understanding of dark matter and dark energy.